عادي خذ وقتك.
اوكي جاهزين؟
اي والله جاهزين الصراحة. انا يعني صدعت وانا احاول افهم.
اول شيء قبل لا نبلش اللقاء حبيت اول شيء اشكر رنيم ان اعطتنا الفرصه كجروب كلنا نتجمع في مجموعه ابان، والشكر هذا مو بس لانه حطت لنا بلاتفورم كلنا نتجمع وناس مهتمه من نفس البيئه في الفيزياء، لكن كذلك شكر لان خلت لنا فرصه ان انا مثلا كان ودي اقرا بيبرز بس دائما اتعيز، بس بسبه وجود هالمجموعه وان انا I'm committed to do a presentation صرت ادور بالبيبرز وحاولت ادور بيبر مناسبه فخلتني اقرا اكثر من ورقه وحتى المراجع وكذا. فبس هذا حبيت اشكر رنيم والجروب كله على المجهود والفرصه. ثانيا بندخل بالموضوع مباشره الحين. وفي تنويه عندي، انا اعتذر من الجروب ان وحتى لو احنا رفعنا الفيديو انه راح يكون اكثره بالانجليزي من جانبي، لاني متعود انا اشتغل مع هالكونتنت بالانجليزي، فاسهل لي اني اتكلم بالانجليزي. لكن اذا في اي شيء مو واضح، جمله كلمه فكره، اتمنى توقفوني وتسالون. وطبعا اوبن ديسكشن، انا مجهز برزنتيشن بس ان اوبن ديسكشن، اي شيء مو مفهوم بالورقه، اي شيء مو مفهوم بالترتيب اللي احنا بنقوله بتكون الاسئله مفتوحه. فيلا نبدا. هذه البيبر اسمها Generalized Uncertainty Principle and Localization in Discrete Space by بوجولد and كيمب. انا اخترت البيبر لان بوجولد كان دكتوري ايام البكالوريوس وهو اللي علمني General Relativity Special Relativity، ف being able to read his paper was a big step for me. هذا ليش اخترتها. والسبب الثاني اني اخترت البيبر لاني احس انها تتكلم عن اشياء مر علينا من قبل، بس it takes it a step further، ممكن تساعدنا ان نتعلم اشياء جديده. فهذا الاوفر فيو مال البرزنتيشن. انا راح ابلش اعطيكم موتيفيشن على ليش ان البيبر هذه مهم، شنو الافكار والثيمات اللي نحتاجها. بعدين راح نغطي البيسك برنسبلز، هذه راح تكون اختي بركه هي اللي راح تمسك هذا الجانب. بعدين انا راح ادخل بالانفستيجيشن which is basically the paper itself. بعدين the takeaways or the
يحيى اعتقد انك حطيت ميوت. الى
الو
ايوه الحين في صوت.
How long have it been muted من البدايه ولا؟
لا بس
من اخر فقره من السلايد اللي قبل.
اي فبنغطي الكونكلوجن والحين بندخل بالموضوع مباشره. باختصار انا ببلش من قصه الفيزياء يعني العامه، وشنو برايي انا كيحيى what really interests me and intrigues me about physics. Okay, I think physics من ايام نيوتن the greatest achievement or what we're trying to achieve or the pinnacle of physics is getting an understanding of a certain kind of grand unification of all physics. Okay, that's kind of misleading لأن people don't believe in the theory of everything and that we might find it or not. Does it really exist? Is it a fundamental thing about our universe? I mean, it's an open question, but going back to the olden days من أيام نيوتن، أعتقد عظمة نيوتن تبتدي بقدرته. عفوا كأنه في صوت داخل. هاي أعتقد أن عظمة نيوتن في قصة التفاحة المشهورة اللي وايد ناس تأذت منها في المرحلة الابتدائية والمتوسطة وثانوي. عظمة نيوتن هو قدرته على رؤية أن التفاحة والقمر ما يختلفون عن بعض، both of them follow the same dynamics, the same kind of theories. Even though they look different, they're kind of the same. They follow the same dynamics, the same kinematics, and the same kind of theories. Okay, so that's the first step of physics. So it was a certain push to an understanding of a certain kind of unification, something that governs the world of heavens and the world of humans, basically. And then I think the second major step in these kind of unification ideas is what Maxwell came up with, which is basically a realization that electricity and magnetism are not, even though they're a different manifestation of the same field, but they come down at the end to being the same field, which is electricity and magnetism, which is another angle of looking at stuff. Even though magnetism might look different, electricity might look different, but in the end, they got married into something called electricity magnetism in an understanding of طبعا a unification in terms of fields. بعدها Albert Einstein, what actually inspired him to follow through with special relativity is his realization that electricity and magnetism are no different from throwing a ball. The physics should be the same. The physics should be invariant. Why, when we do the Galilean transformation, we're not getting the same physics for electricity and magnetism? And that's what pushed him toward special relativity. And then, in a way, he unified time and space, and we got space-time. And then he unified energy and mass, and they are actually the same thing, but they're different manifestation of the same thing. And there are certain transformations where you can go from energy to mass and vice versa. The same thing with time and space. So the underlying principle seems to be that unification seems to be, I'm not saying definitely it is, but it seems like when we think about this universe, we always try to unify stuff and see the symmetries and the similarities between laws and nature. Then the next step, the big step in physics, in my opinion, was the Standard Model. Unfortunately, they chose a really bad name. It's not good for advertisement. It sounds really boring, but this is really amazing. This is our periodic table as physicists. It's one of the simplest periodic tables in the history that was ever made, where you classify everything that exists in the universe into bosons or force carriers, or fermions, which are matter particles. Okay, and they have certain interactions. And the amazing thing is the Standard Model was derived based on the quantum field theory, which stems from quantum mechanics before that. So, I mean, the biggest thing about all of that is that the realization that all particles, that particles and waves and all this talk of duality between them, and we're kind of not being able to tell if particles are real or waves are real because of the quantum mechanical effects. Well, what became apparent is that fields are the real thing. There are an electron field, there are photon fields, there are gluon fields, and everything we see is a mere manifestation of these kind of fields. So all there is in the universe are these fields and extra stuff. The extra stuff, which we're going to concentrate on with the derivation here in this paper, is gravity. Gravity doesn't seem to be compatible with the Standard Model. We don't have a particle for it. We don't have a force carrier for it. So it's odd. We would think it should have a field that is assigned to it, and a particle, which is the graviton, which a lot of physicists has postulated. Okay, so basically, the implication of thinking that there must be a field that's assigned to gravity is like space-time could be that field. Okay, and since electricity and magnetism in QED, which is quantum electrodynamics, suggests that electricity and magnetism field should be quantized, The same thing with QCD, which is the gluons and the Z bosons and the W boson has to be quantized. We would expect that space-time should be quantized as well to get gravitons. So the major derivation of this paper, I think, is that if we impose that the space-time is space is discrete. In this paper, they're talking only about space. They're not talking about time. But if we postulate that space should be discrete, first of all, how can we impose this discreteness to space? How can we quantize space? Okay, and what kind of implications would we get? And here they investigate the implications on the uncertainty principle that comes from Heisenberg, essentially. So this is the motivation of the paper. Now I'm going to give the mic to Barakah, and she's gonna talk a little bit about the basic principles that we think they're important in order to understand this paper. And they're actually basic principles. They're stuff most physicists, as you guys have been exposed to. And we will see that even though the paper might look complicated, it stems from stuff that we're really familiar with. So تفضل يا بركة.
أهلا. ألو، صوتي واضح؟
واضح.
أي واضح.
أول شيء ببدأ كلامي بسؤال. What really define quantization أو الquantum mechanics mathematically؟ إحنا دائما نقول quantization ونتكلم عنها ونتكلم بعد عن كيف نربطها بالgeneral relativity. بس إيش بالضبط تعتمد عليه الكوانتيشن بطريقة رياضية؟ هل هو مثلا superposition أو uncertainty أو مثلا entanglement؟ أحد عنده جواب؟ أوكي. الكوانتيشن يعتمد على الكوميوتيشن relation between the position والmomentum. Once imposed, this relation quantum mechanics follow. طيب كيف uncertainty principle is defined based on the commutation relation since position and momentum is not commutating. احنا نعرف ان الx والp الposition والmomentum ما عندهم function anymore. احنا كنتيجة لهذا زي اللي طورناها أعطيناها upgrade كده we promote it to functions we promote it to operators or matrix and then superposition and other precisely result follow naturally from the linear algebra. زي مثلا في السوبربوزيشن احنا نعرف ان الماتريكس act on vectors which mean that our state is defined as a vectors. So it's allowed superposition. بعد الentanglement follows naturally as taking the tensor product of Hilbert spaces is allowed mathematically. طيب الحين خلينا ناخذ كذا خطوة كذا على وراء عشان نشوف صورة أعم وأكبر. بعد بسألكم سؤال. هل في شيء يشبه الكوميوتيشن ريليشن اللي موجود في الكوانتوم ميكانيكس في الكلاسيكية؟
إيش السؤال بركة؟
هل في شيء يشبه الكوميوتيشن ريليشن اللي بين البوزيشن والمومنتوم اللي موجودة في معلش في صوت إذا ما قاعدة أسمعكم إذا كان في أحد يتكلم. سؤالي هل موجود شيء يشبه الكوميوتيشن ريليشن اللي موجود في الكوانتوم ميكانيكس موجود في الكلاسيكية في الكلاسيكال فيزيكس؟
توقف اللاجرانجيان ايكويشن فعلا من ناحية كيف ممكن الأوبريتر أو الديفرنشال نفس الفورم يتطبق على الفانكشن قبل الديفرنشال الآخر.
اوكي. في شيء يشبه له و
عامل هاملتوني.
ايوه يشبه له البواسون براكت في الكلاسيكية يلعب نفس الدور اللي تلعبه الكوميوتيشن ريليشن في الكوانتم ميكانكس. هذا اللي قاعدين نشوفه الحين، هذا البواسون براكت بصيغته العامة. باي ذا واي احنا بنغير الاكس بنغير الكيو الاكس عشان توصف البوزيشن. بنشوف إن لو ناخذ البواسون براكت للمومنتوم وللبوزيشن راح يطلع لنا 1، وهذا يشبه اللي لقيناه فوق قبل، بس اللهم إنه كان موجود I و H بار، بس إنهم يتشابهون. بس هل هو غريب إنهم يتشابهون أو بالصدفة؟ لا، مو بالصدفة. إحنا نعرف إن القوانين الفيزياء بطريقة ما متصلات ببعض، دائما متصلات، وعلى قولتهم يقولون البعض. ما هو صدفة. البواسون bracket play the same role in classical mechanics to the one that the commutation relation play in quantum. As they both وظيفتهم هم كلهم describe the dynamics of the system. وبعد هو موجود فيه map, invertible map between them. It's called Wiley-Wigner map. والحسابات اللي المحسوبة محسوبة بدقة من العالمين هذولي. So بعد ما احنا وصفنا الكونزيشن وشرحناه وشفنا الانالوجي الموجود بينها وبين الكلاسيكال ميكانكس، وصلنا للفيمس Schrödinger equation which describe the dynamics of the wave function. وزي ما نشوف حنا الحين الويف تعتمد على الهاملتونيان. لما نبي نغير في حلول الويف فانكشن عشان نحصل على حلول مختلفة، الحلول المختلفة هذه تعتمد على الهاملتونيان. لما نيجي نغير، نعرف احنا الهاملتونيان مكون من بارتين، البوتنشيال والكاينتيك. احنا نغير في البوتنشيال، كل ما غيرناه نحصل على دالة موجية ثانية أو مختلفة، والكاينتيك يبقى دائما زي ما هو. وهذا اللي سووه في البيبر، وهذا اللي بيشرح إن شاء الله يحيى في investigation section. وبس هذا اللي عندي. شكرا.
يعطيك العافية بركة. قبل لا نحرك الجوانب الأخرى من البيبرز والانفستيجيشن، في أحد عنده سؤال على commutation relation؟
نقطة ممكن نناقشها إذا سمحت.
تفضل.
هل uncertainty principle يعني is it coming from mathematical base ولا experimental base؟ نقطة هذه مرة مهمة نوضحها قبل نبدأ. أنا أعرف شو الإجابة، بس ودي نتكلم عنها للجميع.
شور. هو طبعا أنا بس حبيت أنوه على شغلتين. أوكي. إن شاء الله راح نرجع حق النقطة، بس مثل ما قالت بركة، the main point what we're trying to say here, for example, in quantum field theory, what is quantum field theory? Basically, you start with a classical field theory, and then you impose commutation relations. By imposing that, you quantize the field, and you get quantum field theory. Okay, so what does it tell us? That the underlying principle that implies uncertainty principle, the idea that we have to promote position and momentum to operators, that states can be in superposition, that uncertainty principle comes about, and entanglement. It's a necessary implication due to the mathematical objects we're working with. So the moment we decide that the commutation relation is not equal to 0, we know that x and p can't be functions. They can't be numbers anymore. They have to be matrices. And we know that matrices act on vectors. That's why, and vectors allow superposition. We know that in linear algebra, tensor products are allowed. Therefore, entanglement will be allowed. Also, there is a relationship between commutation relation and uncertainty principle. So uncertainty principle follows the moment you impose commutation relation mathematically on the system. So that's my opinion. I don't know, maybe Mohammed عنده رأي ثاني بأن uncertainty principle might stem from experimental reason.
لا كلامك صحيح انه for every commutation relation there is uncertainty principle. هنا البيس حقها. لكن
صحيح.
في الغالب اذا تم إشارة uncertainty principle يشار لها بشكل مباشر إلى physical quantities زي البوزيشن أو الانرجي أو التايم بشكل مباشر قبل ما يتكلمون الناس عن الماثماتيكال يعني
صحيح.
البيس لها. لأن الماثماتيكال بيس إنه for every commutation relation اللي يعتبر mathematical form purely commutation جاية من الديفرنشال فورم حق الإيكويشنز حقتك في uncertainty principle اللي يعتبر physical. فهنا الليب from the math to the physics تصور.
Yeah, I totally agree. صحيح اتفق. فبالضبط مثل ما قال اخونا محمد ان that was the whole point of this part, the basic principles. We wanted to talk about that commutation relation is the essence of quantization. When we say we want to quantize something, we impose uncertain commutations. Once we impose certain commutation relations, well, everything else follows. وطبعا اختنا بركه سولفت عن الهاملتونيان وراح نتكلم عنه اكثر بالinvestigation. There are smaller stuff in the paper that I wanted to talk about a little bit as a basic principles before going to the investigation, because it always appears in particle physics. It is the main thing in particle physics. It is the best and the most beautiful things in particle physics. It's symmetries. I mean, when we always see the word symmetries being thrown around in physics, in classical mechanics, and electricity and magnetism, and everywhere. But what really defines symmetries? So here I'm just giving an example. It's not a mathematical formula or anything. I'm saying that symmetries, for example, for a circle, if you rotate it around its center, it's symmetric. It doesn't matter how much. If you close your eyes and I rotate it, you wouldn't be able to tell that I rotated it. So this is a symmetry. You can't tell I changed anything. It leaves certain quantities invariant, okay? But symmetries are not necessarily continuous. They can be discrete. So for example, if I have a square, I can rotate it by 90 degrees and you wouldn't be able to tell that I rotated it. But if I rotate it for 20 degrees, for example, you would be able to tell that I rotated it. So we can tell here that the symmetry of the system is discrete. It's not continuous. There is a huge field in mathematics that is concerned with studying symmetries. It's called group theory. It's an abstract mathematical way of looking at symmetries. They try their best not to give examples, but we as physicists, and because most of the audience are physicists, I'm going to talk about it more example-based to convey the idea of how the paper is going to work, and how group theory actually works. But there are certain axioms mathematically that defines a group: closure, association, inverse, identity. But I'm not going to go in depth into it. Whoever is interested can search more about it. But once these axioms are satisfied, you get a group, which is the group is basically the symmetry of the system. Okay. However, I think this is the more interesting part in the paper because they are going to use this thing. For every symmetry, there are generators of this symmetry. Okay, and a very interesting group, a very interesting symmetry called Lie groups. It's very well known in physics. It has a lot to do with how nature works and the symmetry of nature. So that's why we always talk about Lie groups. And these Lie groups are derived from something called Lie algebras. Lie algebras are basically a relationship between components. There is a Jacobian between them, Jacobian identity. Once you take the exponent of the Lie algebra, you can reform the group. I mean, maybe when I say it like that, it seems like, oh, it's abstract math, it doesn't really make any sense. However, I'm going to give examples where you will realize that you have been dealing with Lie algebra and Lie groups all your time in quantum mechanics without realizing this. So for example, SO3 group. It's a 3D rotation of a sphere. Okay. The Lie algebra of this group is called SO3 algebra. Okay, and it is the commutation relations between angular momentum. You've seen that before. Everyone who did quantum mechanics, maybe advanced level, have seen angular momentum relationship. Lx, Ly equals Lz. The nice thing is that when you exponentiate this relationship, every Lx, Ly, Lz, they generate. They are generators of rotation. What do we mean by generators of rotations? When we take the exponential of that and we get the rotation, if we apply it on a certain vector, it's going to rotate by a certain angle. Okay. Now, I'm not going to delve a lot in the mathematics of how you exponentiate a matrix and how you get another matrix, but this is the gist of it. Okay.
Okay. Nice.
Makes sense, kind of.
Yeah, أنا أحس.
Nice. وطبعا another example مثلا أنا ما حطيته هني بس مثلا generators of translation are momentums. So when you exponentiate a momentum, you get a translational operator. And there is something very interesting about the generators and all of that. Once you have a symmetry, once you have a certain symmetry, the implication of that, you get a conservation of a certain entity. For example, when we talk about conservation of energy, when all we think about is that it's a fundamental law about the universe, right? Because we learned it since we were young. But it isn't very fundamental after all. What's fundamental is it's called time symmetry. When time is symmetric, you get energy conservation. It's called Noether's theorem. Whenever you have a symmetry, you have a conservation law. So, for example, if you have a spatial symmetry, translational symmetry, what you end up having is momentum conservation. It's what we do in physics all the time without speaking about the fundamentals of it. But that's the beauty of the symmetries and the group theory and all of that. Okay. So now I'm going to talk about.
معليش قبل ما أتكلم أنا ودي أسأل عن symmetry of time. وش يعني هل ممكن نتفصل أكثر إن ليه إذا صار في symmetry للتايم يصير في conservation للإنرجي وكل شيء ليه؟ يعني أنا ودي.
نايس. طبعا هذه رياضيا مثبته تقدر تدور على شيء يسمونه Noether's theorem. انا راح ادزها بالجروب. اوكي. Basically she does it in a rigorous mathematical way, but basically the gist of the idea, once you have a certain symmetry, forget about energy now. Once you have a certain symmetry in your system, what you end up having is a certain conserved quantity without identifying the quantity or the symmetry. Okay. So for example, you have conservation of charge. You think it's fundamental, right? That's how the universe works. But it works because there is a certain symmetry that you were never taught, like in the undergrad level, that it's a certain group called U1, for example. U1, an implication of U1, you get a conservation of charge. You see? So basically, whenever you have a certain symmetry, you end up with a certain conserved. You can label it whatever you want. You want to call it charge, you want to call it energy or whatever. It's irrelevant, but there is a quantity out there. You have to search for it experimentally, and you can get it out. You see? Okay. So we knew that there is a conservation based on experiments a while ago, but we didn't know why these conservations exist. But mathematically, it's a rigorous thing. They've done it before. But they done it in I think in the 50s or 60s. I'm not sure about the date. I'm not a historian, but yeah, it's a very important result in physics. Then, after talking about all of that, now I'm going to delve into the paper. Okay. So he starts. I know the paper looks kind of complicated, but what he really does is what Barakah said earlier. He wants to get this space, okay? And it seems like continuous, what we were, okay. So let me say this. When we talk about quantization, okay, and the commutation relation, what are we quantizing if we're not quantizing space? Can anyone answer me that? Like, we talk about quantization all the time, and right now this guy is saying I want to quantize space or have a discrete space. What did we quantize then in quantum mechanics?
Energy.
بالضبط. We quantized energy, but we never quantized space. Space was continuous, was linear, and that's how the symmetry of the universe seems to be, okay? But it seems like if there is a possibility of quantum gravity and we want to quantize gravity, we need to quantize space itself. So basically, here he tries to impose this quantization on space. It seems like the way we have momentum, if it's continuous and if it's linear, the way we have it, okay, we end up necessarily with continuous space, because as we said, that momentums are the generators of translations, okay? So our problem is that momentum seems to be continuous and linear and all of that. So we're getting necessarily a linear continuous space. So what he imposes is there is a well-known theory in condensed matter called bulk states or periodic potentials, okay? It has nothing to do with what supposedly the paper talks about, but he uses this idea and imposes it to space and sees what he gets, okay? So we know that in condensed matter, they work on lattices, okay? So when we talk about lattices, we're talking about, for example, cubes. They have an end, they're discrete. They're not like a continuous spaces, for example, okay? So what he does here in the paper, he suggests imposing a certain Hamiltonian. As Barakah said, we can't change to change the wave function, because the wave function is the solution of the Schrödinger equation. We know that the only thing you can change in the Schrödinger equation is the potential. So he imposes a periodic potential. So basically, I didn't put the things he wrote. He talks first about getting a periodic space, okay? And then he gets discrete momentums. And then he says, that's the first part of the paper. And then he says, well, that's not what we're interested in. We're interested in the opposite. We have our potential in momentum space, okay? We start with a potential in momentum space, which is periodic. That's why after P naught, which is the period, you get back to your initial potential. He solves the Schrödinger equation and he gets this solution for the wave function, okay? And it is periodic. The wave function is periodic, okay? It doesn't change over the period. You go back, you only get a phase, okay? And the funny results, okay, so then basically you're having your momentum as periodic or circular. As a result of that, he talks about it in the paper, you get discrete spaces, and it's okay. Like that's the result of bulk states, and they knew it the whole time. However, his investigation is about quantizing space. So now he has discrete spaces, and he asks the question, what happens to the uncertainty principle? Does it stay the same? Does the commutation relation stay the same? And the odd results is basically he does a lot of calculations in the paper, but he ends up having that the uncertainty principle can go to zero if we're working with discrete spaces for space. So you can localize, you can get the exact result of, you get the exact position of certain particle without getting any uncertainty, which is very odd in terms of quantum mechanics. It doesn't sound very compatible with the uncertainty relations. And the result of that, he talks about reforming the commutation relations to be compatible with the results. And guess what? It actually is. There is a whole calculation, and there is another paper I sent that I said it's kind of it's supported mathematically because it gives a more general way of looking at stuff. But before going into the commutation relations he imposes and all of that, I wanted to go back to the idea of Lie algebra for a second and show you that you have been working with Lie algebra without knowing, but because you weren't given this label. But the commutation relations are the Heisenberg algebra. It's a relationship between components Q, P, and 1, which is the identity. And there is this relation. And you take the exponential of that, and you get the Heisenberg group, and it acts on Hilbert space. And you've been working all the time with all of that, but you didn't know it's called Heisenberg algebra, but it is Heisenberg algebra. And basically in the paper, how does he get the generalized uncertainty principle? He goes back to the generalized Heisenberg algebra. So he goes back to the fundamentals of math of the Heisenberg algebra, and he rederives the whole uncertainty principle based on this. So basically that's what he does. He goes back to the other paper that I've sent. They do precise mathematical induction methods on the Heisenberg algebra, and they end up with this uncertainty relation. This is the more general uncertainty relation, commutation relation. And the commutation relation, as Muhammad said, is actually directly connected to the uncertainty principle. And we have this uncertainty principle, which gives this relationship, and which makes you suspect that we're getting delta Q equals to 0 because the commutation relation wasn't general enough. The one we were working with wasn't general enough. Therefore, we have to modify the commutation relations, so we should have a different alpha and a different beta here. Does it make sense so far? Anyways, so again, the paper has a lot of math, but you realize he used Poisson brackets. He does the whole Lie algebra, and because Lie algebra is connected to the Poisson algebra, as the one we showed earlier, which is 1 over IH bar multiplied by the I don't want to make a mistake there, but I think multiplied by the commutation relation gives you the Poisson bracket. That's why he starts with a classical mechanic notion of phase space. We all learn phase space at some point, which is basically describing a certain particle in space and momentum. This is called phase space. So, for example, the phase space of the pendulum looks like that. So, for example, when the position is 0, here you have the maximum momentum. When the position is the farthest, here you get momentum equal to 0. Okay, okay, I'm flipping the notions, but yeah, you get what I'm trying to say. Okay, so yeah, when position is farther, velocity is 0, therefore momentum is 0. So he basically says what he does in the phase space. He says that okay, we are imposing a circular or a periodic momentum, right? Well, let's think about it more of an angle. It's going to be easier. So his phase space is described by an angle, which is the sine and the cosine, and the position, where P naught is the periodicity. Okay. And basically what he does, he realizes that sine and cosine are not the most convenient things to work with to do the commutation relations and the Poisson bracket and all of that. He decides to define H and H star, which is if you take the addition of them, you get I guess cosine, and if you take the subtraction of them, you get sine or the opposite. I'm not sure, but there is because you know that exponential gives you a cosine plus I sine, and here it gives you cosine minus I sine. And then there is a certain relations, and here we get a clean momentum algebra. So he basically just what he decides to do, instead of doing a momentum position commutation relations, he does a relationship between position and H. Obviously, you think, oh, this is odd. Why does he do that? But you've seen it before in physics. For example, the relationship between A and A dagger, the ladder operators. It's just you use them because they have a certain, they're easier to work with mathematically, they have a nicer result. So he only redefines position momentum with a certain new operator, and he takes the algebra of the new operators, which is just like the Heisenberg algebra, but this is the moment algebra. And based on it, he rederives the uncertainty relation. So basically, that's what the paper is doing. He really defines everything in terms of H. He takes the commutation relations, and then he re-relates them to the uncertainty principle of position and momentum. Okay, and then he gets this shocking result. This is the commutation relationship average, and that's what you get. And what do we realize here? That if delta P is equal to 3P naught over T pi squared, this goes to 0. So it actually makes sense that delta Q is equal to 0. So basically what he did, he took quantum mechanics, he took quantization, and he rederived the commutation relation, and he quantized space, and he did the commutation relations on quantized spaces, and that's the result of the uncertainty principle. And now, well, what does this have to do with gravity? What does this have to do with quantum gravity? Well, that's the conclusion of the paper, because here it's not my expertise, but that's basically what he does say, is that delta V here describes the total volume of an isotropic universe model, and P, the expansion rate or the Hubble parameter, okay? And he just changed the variables, but that's what they use in loop quantum cosmology. And the moral of the story in the end is that he rederived the uncertainty principle for the universe if the universe happened to be if we happen to live in a universe where space is discrete and momentum is periodic. But basically there is also a caveat that I didn't say, but in order for him to do all this derivation, and you're going to see a nasty derivation that he does in the paper, in order for them to do this derivation, they have to assume that P and delta P is small compared to P naught, which is the periodicity, because he does certain expansions, Taylor expansions, and such, and the assumption has to be that P and delta P are small compared to P dot. And here we're using the large P's, which is the expansion, the Hubble parameter, but you can still say the same thing about P here and delta P here and P dot. Delta P has to be smaller than P dot, and basically that's the paper. I hope you liked the presentation. I don't know if I went over it pretty fast, but we can open the platform for questions. I hope you like it. If you have questions about the paper directly or the presentation, go ahead. Go ahead and ask questions.
يعطيكم العافية، رائع جدا. والربط مرة عجبني في الأخير، كيف ربطنا بالانسرتينتي بالنسبة على طول بشكل مباشر من الديريفيشن.
الله يسلمك يا حبيبي. ان شاء الله اهم شيء انه واضح البرزنتيشن والافكار والورقه ممكن تكون شويه تكون مفهومه اكثر بهالطريقه.
معليش يحيى، انا عندي سؤال.
تفضلي.
في الابستراكت تبع البيبر كان مكتوب انه نشتق علاقات مبدأ الشك من خلال التمدد لحظي للنظام الكمومي عندي، وتعطينا periodic momentum. إيش يعني الزخم الدوري هنا؟
سوري، can you repeat؟ الصوت يقطع. شلون؟
من البداية.
سوري، قاعد تقولي ما أدري والله، ما سمعت عدل، ممكن تعيدين؟
طيب أوكي، بقول إنه في الابستراكت تبع البيبر بيقول إنه إحنا بنشتق علاقات مبدأ الشك من خلال مدد اللحظي للنظام الكمومي اللي بيكون عندي، بالتالي تعطينا periodic moment. إيش يعني الزخم الدوري هنا؟
الزخم الدوري بالضبط بالضبط اللي كنا قاعد نتكلم عنه تو. الزخم الدوري here يقول basically as we see so here in the momentum itself. Sorry, let me go back here. Yeah, here. Okay. So he assumed that the momentum is periodic. مثلا forget about how you, okay, I know it's hard because when you think about momentum, you think about continuous and linear thing, okay? But what he's imposing, what if momentum was periodic, was just like a sine wave, okay? Just like زاوية. بالضبط, that's what he does. يستخدمها كزاوية. What if it was like just an angle out there, okay? And it only repeats. It doesn't change. Even though if you get 4 pi, it's still divided into pi. You get pi, 2 pi. Let's go other. Then okay, you're gonna get a different number when you divide it. But then if you take a sine and a cosine, then you think about it as an angle. So basically, that's what he does. He imposes that momentum is an angle. It's circular. It's periodic. And then based on that, he realizes, oh, if you just impose this fact, if you say that we're working with a periodic topology, with a circular topology, the moment you say that, discrete spaces are they pop out because the math just works. When you have a periodic momentum, because you have a momentum, how is momentum related to position in quantum mechanics? They're related by a Fourier transformation, okay? And the Fourier transformation of a periodic system is discrete. معي؟
Okay.
فهو basically he knows that momentum is periodic. He knows how to Fourier transform a periodic system because we know how the math works. He gets a discrete position, and that's what he does in the paper. Explicitly.
شكرا.
حياك. أي سؤال آخر؟
طيب يحيى أنا عندي سؤال.
تفضل.
يعني الحين إحنا الحين توجد عندنا discrete space بعد هذا كله اللي سويناه صح؟
Yeah, we got a discrete space.
طيب أنت قلت برضو ال uncertainty principle goes to zero بعد لما يصير عندنا discrete space. فهل يعني إيش حينتج بعد ده كله؟ إيش حيصير؟
And the uncertainty principle equals to zero.
أيوة أنت قلت من ال uncertainty principle will go to zero.
Yeah, it's just okay. What does it mean? It's just like, for example, in the uncertainty principle, in the regular uncertainty principle, okay, it's not like a big deal, but you realize that you can't localize a certain particle exactly at مثلا zero. Okay, you will always have an uncertainty بالقياس. Okay, because of this relationship. Where is it? Sorry. Okay, if you have this uncertainty principle, it's equal to h bar over 2, you know? So at any point, you know that a delta q can't go to zero. It's just, the whole point is that there is no, I don't know, there is no experimental implication. Okay, there might be an experimental implication if we have عندنا جهاز that realizes that there is no uncertainty while أو يعني ما في أي نوع من variance in the بالقياس. Okay, but it's just a profoundly different kind of mathematical object. That's the whole point of the paper. The uncertainty principle and that we already have, we were working with, or what I liked about the paper, the uncertainty principle we worked with isn't general enough. It's just happened to be a subspace of a larger uncertainty principle, which looks like that. And as a consequence of discrete position, you get an uncertainty principle that looks like that, which allows for a zero delta q. So it's just, I think it's a mathematical implication, but I don't know if there is a groundbreaking implication of that tells you, but it just tells you that, for example, in quantum mechanics, we always say that position and momentum are not like, you won't be able to have, a confidence of 100% when you localize it. But now it seems like if we happen to live in a world where position is discrete, it's doable. But طبعا, obviously you have to put into account for all this math to work that momentum has to be the delta p has to be very small in comparison with the periodicity. يعني مثلا لو انت كان عندك الدلتا p is equal to 2 pi, this result won't follow. So he specifically says that in the paper, that we know that what we did was for specific delta p's, not for general uncertainties for momentum.
اوكي تمام.
هلا حفيك. أي أسئلة؟
لا مرة غريب الموضوع الصدق. نحاول نهضمه شوية.
إن شاء الله على الأقل صار أوضح إلى حد ما، ولا لحد الآن؟
هو الفكرة واضحة لكن تحتاج فهم، وقت الفهم.
إيه لا إن شاء الله. I think now when you read the paper it's going to be more clear the pathway he's taking. لأن لما تقراها
وضحت الفكرة. وضحت الفكرة كيف، لكن هي ما أقول لك هي ما فيها وضوح، هي واضحة لكن هي صعبة الفهم شوية. يعني كيف تتخيل لا يقين يساوي صفر؟
إيه بالضبط.
تحس إنه يعني إيش كذا، تحس يساوي صفر إيش بس تحس فيه.
صحيح مو اعتيادي.
إيه مو اعتيادي أبدا.
بالضبط. هذا ليش أنا يعني البيبر اخترته، لأنه it was a shocking result for me. Like I didn't expect to get this outcome.
بس مرة interesting، مرة interesting جدا.
شكرا. طبعا هم الله بركة مشكورة وايد ساعدتني في البيبر واشتغلت عليها، ويعني يعطيها العافية. أنا اخترت شوي بيبر a little advanced بس she tried her best which is amazing.
والله يعطيكم العافية كلكم، بركة ويحيى، جدا موضوع حلو وجميل، وتعبتوا على الشرح، جدا جميل شرحكم، يعطيكم العافية.
الله يعافيك. شكرا.
يعطيكم العافية جميعا.
شكرا. اللي جدا أشكرك يا يحيى، وجدا أشكرك يا بركة على الفرصة إني عرفت شيء زي كذا، لأن صدق يعني أعتذر عن عدم المشاركة بس لأني أنا جدا مصدومة ومبهورة من الموضوع. بعطي نفسي أسبوع أقرأ الورقة العلمية بشكل عميق أكثر عشان أفهم الموضوع بشكل أكثر. مرة أشكركم على الفرصة إنه أعطيتونا شيء جديد يعني نحط تفكيرنا فيه. جدا شكرا.
الله يحفظكم. شكرا. أنتم شكرا على الفرصة.
الموضوع جدا حلو، مرة استمتعت الصراحة، بس صادقة لأني يبغى لي وقت يعني زيادة عشان أفهم أكثر، بس جدا استمتعنا. شكرا مرة.
ونحتاج وقت في البروسيسنج الانفورميشن الحلو هذا.
بس إن شاء الله ربع الثيري حبوا الموضوع وربع الإكسبيرمنتال ما ملوا من الموضوع. خصوصا محمد إكسبيرمنتال الحين.
لا ما ملينا إن شاء الله.
لا جدا رائع، مرة جميل. أنا مرة أحب الثيري تعطيك يعني أكثر شيء ممكن أحب الثيري فيه إنه يعطيك يخفف لك الصدمة الموجودة في الإكسبيرمنت، يعني بدون الماثيماتيكال ريليشنز بالكوميوتيشن والأشياء الديب ماثيماتيكال فورمز. لو رحت على طول الانسرتينتي برنسبل قاعد تفهمها من ناحية البراكتيكال أو الإكسبيرمنتال بارت أو أسبكت، ما راح تكون انتويشن مناسب بدون ما
ريلي ويرد.
اي بالضبط
صح.
فدائما الماثماتيكال بيس لاي شيء يعطيك ديب اندرستاندينج ويخفف لك الشك اللي ممكن تحصل عليه.
صحيح
يعطيكم العافيه.
يعافيك.
فعلا الله يعطيك العافية يحيى، ويعطيك العافية بركة بعد. يعني أنا ممتن صراحة، أحس نقلتني لي يعني أنظر ريلم. أحس لي هذا موجود في الواقع، فشكرا صراحة. وأحس يعني فتح لي أبواب كثير ممكن أبحث فيها وتزيد. نقطة السيمتريك مرة انترستينج صراحة. يعني دائما كنت أفكر إنه ليه كذا قاعد تصير، يعني ليه جاي كذا، يعني خلق كون وصار فيه قوانين ثابتة وما ندري ليه. الله يعطيك العافية، جدا رائع.
حياكم.
شكرا لكم. شكرا.
في أسئلة ولا خلاص؟